Neutron stars are fascinating celestial objects that challenge our understanding of physics and the cosmos. Formed after the explosion of a supernova, these stars are the remnants of gigantic stars that have exhausted their nuclear fuel. However, while we know how they form, the mysteries surrounding them are deep and perplexing. Imagine a sphere that, despite being about the size of a city, contains more mass than our Sun. How is it possible for something so small to be so heavy? Neutron stars are the result of gravitational collapse, where the pressure of gravity is so intense that electrons and protons combine to form neutrons. But what happens inside them? Neutron stars spin at astonishing speeds, some rotating hundreds of times per second. This is not only a cosmic spectacle, but also challenges the laws of physics as we know them. What force keeps their rotation at such speed? What effects does it have on the space-time around them? Moreover, there is the intriguing idea that on their surface there may be mountains the size of a millimeter, but with such enormous mass that their gravitational effects would be devastating. How can a small bump have such a monumental impact? Even more puzzling is the mass limit that a neutron star can have before becoming a black hole. There is no consensus among scientists on how much mass is too much, raising one of the most fundamental questions about the nature of the universe. Why is there a limit, and what does this mean for the evolution of stars? The gravity surrounding these stars may also be weaving gravitational waves that we have never detected. Imagine a sea of invisible waves propagating through the cosmos, which we have yet to capture. To add to this, pulsars, a special type of neutron star, spin with impressive precision, almost like cosmic clocks. However, the mechanism that makes them work remains an enigma. What secrets lie behind their regularity? The surface of a neutron star is also a mystery. Do they really have a solid surface, or is it something completely different? This question leads us to reflect on the very nature of matter and the behavior of physics in extreme conditions. Astronomers have also observed sudden changes in the rotation speed of some neutron stars, a phenomenon known as glitches. What causes these unexpected changes? Additionally, there are neutron stars that seem to come back to life by absorbing material from other stars, turning them into true zombie stars. How is it possible that after collapsing, they can experience a rebirth? The matter in the core of these stars is so dense that it could contain the most extreme form of matter in the universe, but we will never be able to see it directly. What implications does this have for our understanding of physics? In the end, it is unclear what the final fate of neutron stars will be. Will all of them become black holes? Or will some extinguish in a different way? Moreover, around some of these stars, cosmic echoes have been detected, mysterious signals that could reveal phenomena not yet understood. What stories do these signals tell? Finally, even though they cool faster than expected, suggesting unknown processes within them, the nature of their atmospheres, the extreme magnetic fields they generate, and the possibility of strange quarks existing within them leave us with more questions than answers. What new revelations await us in the study of these enigmatic stars? This is how neutron stars continue to be a labyrinth of secrets, challenging our understanding and pushing us to explore beyond the limits of what we know. Are you ready to dive into these cosmic mysteries? Neutron stars are fascinating and enigmatic objects that challenge our notions of physics. One of the most surprising aspects of these stars is their extreme rotation speed, but what does it really mean to spin hundreds of times per second? Imagine a spinning top that rotates rapidly and instead of stopping continues to spin at an astonishing speed. Neutron stars are like that top, but much more intense. The force of their rotation is so powerful that it has led scientists to question the limits of physics as we know it. The question that arises is, how is it possible for such a massive object to spin so quickly? The answer seems to lie in a phenomenon called conservation of angular momentum. When a massive star explodes and collapses into a neutron star, its core contracts so much that its rotation accelerates dramatically, similar to how a figure skater spins faster when she pulls her arms in. This produces a spectacular effect, where some of these stars can spin more than 1,000 times per minute. But what happens inside these rapidly rotating stars? The extreme rotation is not only fascinating because of its speed, but also because of its consequences. Astronomers have discovered that this rapidity can influence how they behave, generating radiation in different wavelengths from radio to X-rays. This leads us to another intriguing question. How do these fast rotations affect the internal structure of the star? Some models suggest that rotation can distort the core, creating an environment where matter behaves in ways we do not yet fully understand. On the other hand, the impact of these speeds on the life of a neutron star is astonishing. As they spin, these stars can emit regular pulses of light, known as pulsars. This occurs because their rotation creates a cosmic lighthouse that emits radiation into outer space. But what makes some of these pulses so precise? Pulsars, a type of neutron star, are famous for their regularity, almost like a cosmic clock. However, what internal mechanism allows for this precision? As we delve deeper into the mystery of rotation, we encounter another intriguing phenomenon: microscopic mountains. Although it sounds strange, some theories suggest that these stars may have mountains that, in terms of scale, are only about a millimeter in size. However, these mountains are made of extremely dense material and could have immense masses. But how is it possible for something so small to generate such a significant influence on the star as a whole? The gravity in these stars is so intense that any irregularity, even one so tiny, could have devastating effects. The gravitational force could amplify vibrations and alter the behavior of the star. This leads us to question, if neutron stars have these small mountains, what other secrets could be hidden inside them? The answer could change our understanding of matter and gravity. As we explore these mysteries, we also encounter the exact mass limit that a neutron star can have. It is an enigma that has puzzled scientists for years. It is believed that there is a critical point at which, if a neutron star exceeds a certain mass, it will transform into a black hole. But what is that limit? Estimates vary, and each new observation challenges what we thought we knew. This raises an even deeper question: what defines the ultimate fate of a neutron star? The extreme rotation and density of these stars are not only an impressive spectacle, but also open the door to new theories about the nature of matter. Inside, there could be unknown interactions that challenge our current understanding. This leads us to question the very structure of matter itself. What is really inside a neutron star? Could there be exotic particles that we have not yet discovered? Exploring these mysteries leads us to consider how the universe behaves on its most fundamental scale. Every answer we find generates new questions, and the cycle of discovery never stops. As scientists continue to observe and study these stars, new possibilities arise for understanding the processes that govern the cosmos. The rotation speed of neutron stars is just the tip of the iceberg in a sea of enigmas that still need to be unraveled. In conclusion, neutron stars are a testament to the wonder and complexity of the universe. Their extreme rotation speed not only challenges our notions of physics, but also invites us to look beyond the known. As we continue to explore these mysteries, each discovery brings us one step closer to understanding the very essence of the cosmos. The search for answers continues, and the journey into the unknown has only just begun. If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this star odyssey. What if I told you that some neutron stars can have mountains, but not mountains like those we know on Earth, rather small elevations that, despite their tiny size, contain immense mass? How is it possible for something so small to be so heavy? The answer lies in the incredible density of these stars. Inside them, gravity is so intense that it compresses matter in such a way that what we consider light on Earth becomes an overwhelmingly heavy object here. Let's think about this. A neutron star, which is the remnant of a supernova, has a mass that can be up to twice that of the Sun, but compacted into a size of just about 20 kilometers in diameter. This means that all that material is compressed into an incredibly small space. Now imagine that in this space there are mountains that, although only a millimeter high, are made up of mass that could rival that of a mountain on Earth. How do these microscopic mountains form? Scientists have theorized about the existence of these formations due to the unusual conditions within a neutron star, as material is compressed by extreme gravity. Irregularities can develop on its surface. These irregularities, though minimal, can result in mountains that, in terms of gravity, have a much more significant effect than we might imagine. But why are these mountains important in the context of physics and astrophysics? The answer is fascinating. These elevations can influence the rotation of the neutron star, which in turn can affect the emission of radiation that we observe. When a neutron star spins, the tilt of its axis can create variations in the intensity of the signals it emits. This translates into light patterns that can be observed from Earth. Can you imagine how these small mountains might be affecting what we see in the sky? Now, even though we have theorized about these mountains, we have never been able to observe them directly. This is because the conditions inside a neutron star are so extreme that matter behaves in ways that challenge our current understanding. Is there something more to these microscopic mountains that we have yet to discover? The truth is that science still has many unanswered questions. We might ask ourselves, if these mountains exist, what else could they reveal to us about the nature of matter in the universe? By studying these irregularities, we could gain insights into how matter behaves under extreme gravity conditions. It would be like opening a window to a new world, where the rules we know do not apply and where physics manifests in ways we still do not understand. Moreover, understanding these mountains could have broader implications for our understanding of the universe. If we manage to unravel the mystery of neutron stars, we could also gain a better understanding of phenomena like black holes and other celestial bodies. What other secrets do these dwarf stars hold for us? It's an intriguing dilemma, isn't it? On one hand, we have the fascination with the mysteries of the cosmos, and on the other, the need to obtain answers that could change our perception of reality. The microscopic mountains on neutron stars are just a small part of a much larger puzzle, and each new piece added brings us one step closer to understanding the universe. The existence of these mountains also raises questions about how they form and how they influence the evolution of neutron stars. Could they be indicators of a star's history, its collisions, and its merging with other celestial bodies? Each discovery in this field could be a thread that leads us to unravel the history of the cosmos. And let's not forget the impact this research could have on technology and science here on Earth. As we learn more about the physics governing these stars, we could develop new technologies and innovations that change our daily lives. Who would have thought that studying a neutron star could lead us to advances in computing or energy? In summary, the microscopic mountains of neutron stars are a reminder that there is much more to discover in the universe. Each of these enigmas invites us to look beyond what we know and challenge our perceptions. Perhaps in the future we will be able to unravel the secrets that these stars hold and answer the questions that continue to intrigue humanity. Are we ready for the challenge of knowing the unknown? The answer lies in the sky, waiting to be discovered. What is the exact mass limit that a neutron star can have? It is a question that has intrigued astronomers for decades. When we look at the sky, we find these fascinating stars the result of supernova explosions, which compress the core of a massive star into an incredibly small space. But how far can they go? How much weight can they bear before gravity traps them in a black hole? Neutron stars are incredibly dense, much more so than any other type of star. It is estimated that a single spoonful of matter from a neutron star would weigh as much as an elephant. But in this case, we are not just talking about density. We are discussing a critical point, a threshold that can determine the fate of these fascinating cosmic entities. If the mass of a neutron star exceeds a certain limit, known as the Tolman-Oppenheimer-Volkoff limit, it would collapse under its own gravity, turning into a black hole. However, this exact limit remains a mystery. What factors determine this limit? Is it the composition of the material inside or the speed at which it spins? Perhaps a combination of both. The truth is that as scientists investigate more about the internal structure of these stars, they discover that there is much more than meets the eye. The matter in their core can behave in extremely unusual ways due to the intense gravitational and nuclear forces at play. Imagine that inside, matter does not behave as it does under normal conditions. Particles can fuse and form new types of matter that challenge our current conceptions of physics. Theories have been proposed suggesting that at the heart of a neutron star, strange quarks could exist, even more exotic particles that could change our understanding of matter itself. But how could this affect the mass limit of a neutron star in our quest to understand the mass limit? It is essential to consider how these stars form and what processes may be at play during their evolution. When a massive star exhausts its nuclear fuel, it collapses into a supernova, leaving behind a neutron star. But what happens if this star begins to accumulate more mass through fusion with a nearby star, or by capturing matter from the surrounding space? Could it exceed the critical limit and transform into a black hole? Some studies suggest that the mass limit is not a fixed number and can vary. Factors such as the star's rotation and its interaction with the environment can influence this threshold, adding a level of complexity to the situation. Could different neutron stars have different mass limits? This possibility opens a range of questions about the unique properties of each neutron star and their evolution. Observing neutron stars in binary systems, where two stars interact with each other, may provide clues about this limit. In these systems, a neutron star can steal material from its companion, increasing its mass and potentially approaching the critical limit. However, how this process unfolds and its effects on the structure of the neutron star remain subjects of research. Moreover, neutron stars emit radiation and phenomena that we could study to better understand their nature. Gamma-ray bursts, for example, are events that can be associated with these celestial bodies. But could these bursts indicate that a neutron star is nearing its mass limit? This relationship between explosive events and imminent collapse is a fascinating area of study. The search for answers is not just an academic question. Understanding the mass limit of neutron stars could help scientists unravel the mysteries of gravity and physics under extreme conditions. As technology advances, our capabilities to observe and measure these phenomena also improve. Each discovery could bring us one step closer to unveiling the enigma surrounding these cosmic objects. Meanwhile, the question of the mass limit of neutron stars remains without a definitive answer. Are we facing a phenomenon that challenges our current theories of physics, or are there factors we have yet to consider? The scientific community continues to investigate, and each new finding brings more questions than answers. The search for this limit is not merely an academic exercise. It helps us understand our position in the vast universe and how the forces that govern everything around us work. Neutron stars are a reminder that, despite the advances we have made, there is still much to discover. In the grand scheme of things, how many more secrets do these dense and mysterious stars hold for us? What else can we learn from them in the future? The fascination with neutron stars lies not only in their extraordinary nature, but also in the profound questions they raise about the universe and our existence within it. As we continue to explore the cosmos, each discovery brings us closer to uncovering the secrets that these stars have to offer. What if I told you that within neutron stars there could be a phenomenon as enigmatic as gravitational oscillations? These oscillations are variations in the intensity of the gravitational field that might be occurring inside these dense stars. But what does this really mean? Imagine a calm sea that suddenly starts to stir. That agitation could correspond to gravitational waves forming inside a neutron star, but so far no one has been able to detect them. Why is this phenomenon so important? Gravitational waves are like echoes of the universe, revealing cosmic events happening billions of light years away. But in the case of neutron stars, the mystery deepens even further. These oscillations could be continuous, meaning they are not just isolated events, but a kind of cosmic hum that is there, in the background, waiting to be heard. But why haven't we been able to capture this sound of the universe? The answer may lie in the very nature of neutron stars. These stars are so dense that a teaspoon of their material could weigh as much as a mountain. That extreme density could be complicating the detection of the gravitational waves forming within. In this sense, neutron stars are not only fascinating for their composition but also for the secrets they hide in their depths. Imagine that gravitational oscillations are a cosmic dance. Every movement, every turn could be sending signals through space. However, the tools we use to measure and understand these oscillations are still not up to the challenge. Science advances, but the universe has its own timing. It's as if we are trying to listen to a melody while the wind blows in our direction, distorting what we really want to capture. Some scientists suggest that the key to understanding these oscillations could lie in the way neutron stars interact with each other. When two of them come close, gravity intensifies, causing their oscillations to mix. This could create a new type of gravitational wave, a cosmic symphony that we could study. But will our current technology be sufficient to capture those echoes? Another intriguing question is, what would these waves tell us if we could hear them? They could reveal information about the internal structure of neutron stars, about how they are composed and how they behave under extreme conditions. Perhaps they would even give us clues about the evolution of the universe itself, but at this moment, they remain an enigma, a mystery that continues to elude us. As astronomers continue their search, we find ourselves in a curious position. We are on the brink of a monumental discovery, but nature has left us with a puzzle we cannot fully solve. Science never stops, and every day new advances are made in the detection of gravitational waves. However, neutron stars with their mysterious oscillations remind us of how vast and incomprehensible the universe is. Meanwhile, the question persists, will we be able to unravel these secrets? Human curiosity drives us to move forward, to keep exploring and seeking answers. Deep down, the search for these gravitational oscillations is not just a scientific quest, but also a search for our place in the cosmos. What discoveries await us on the horizon? It is fascinating to think that despite our limitations, we continue to try to decipher the secret codes of the universe. Neutron stars are a reminder that there is always more to learn, more to discover. As telescopes and gravitational wave detectors become more sophisticated, perhaps one day we will be able to hear the murmur of those gravitational oscillations. What will they tell us then? Ultimately, the mystery of gravitational oscillations invites us to reflect on the very nature of science. Every answer we find opens the door to new questions. Every discovery leads us down a path filled with intrigue and fascination. The search for these gravitational waves in neutron stars is just a small part of a much larger journey. A journey that, with each step, brings us a little closer to understanding the vast universe that surrounds us. The future is uncertain, but that is what makes it exciting. The exploration of the cosmos is an adventure that has no end, and neutron stars are just one of the many mysteries that await us. So let us move forward, with the hope that one day, perhaps, we can unravel the secrets that have been there, hidden among the stars, waiting to be discovered. Neutron stars are fascinating objects in the universe, and among the many mysteries that surround them, there is one that has captivated the attention of astronomers and curious minds alike: the enigma of pulsars. But what exactly are pulsars? They are neutron stars that rotate extremely quickly and emit pulses of electromagnetic radiation. But how is it possible for these stars to act as such precise cosmic clocks? Imagine a star that spins hundreds of times per second, emitting radiation regularly, like a lighthouse in space. That's what pulsars do. But why do they behave in such a singular way? The answer seems to be related to their intense gravity and rapid rotation. The combination of these factors creates a magnetic field so powerful that, as it spins, it beams radiation into space. This radiation can be detected from Earth, allowing us to measure its rhythm and, in a way, use it as a clock. However, another intriguing question arises. Why are some pulsars so precise, while others exhibit variations in their pulses? Some pulsars are so stable that their rhythm can be used to study cosmic phenomena, such as the movement of planets in distant systems. Yet, despite their precision, we still do not fully understand how they manage to maintain that regularity in their pulses. The nature of their emission also leaves us perplexed. Each pulsar emits radiation at different wavelengths, from radio waves to X-rays. Why this diversity? Theories suggest that this is due to the complexity of their magnetic field and the interaction of the radiation with the star's environment. But what is inside a pulsar that could be causing this phenomenon? Some scientists have proposed that the internal structure of pulsars is much more complicated than previously thought. They are not just dense neutron stars. They may have internal layers that modulate the way they emit radiation. This raises a new set of questions. How did these layers form? What processes occur inside them that allow for this diversity in emission? And speaking of diversity, we cannot overlook the phenomenon of glitches. What are glitches in pulsars? These are sudden and unexplained changes in the rotation speed of a neutron star. These events can occur unexpectedly and often leave astronomers scratching their heads trying to understand what is happening. Why does a glitch occur in a pulsar, and what causes it? The most common theory suggests that these changes may be caused by movements of material inside the star, but there is still no definitive answer. This uncertainty adds an air of mystery about how pulsars really work and how these changes impact their behavior. Another fascinating question is the fact that some pulsars have such regular behavior that they have been used to detect gravitational waves. But how can these stars be so useful in the search for such difficult-to-observe phenomena? The answer lies in their stability and the way their light is affected by the gravity of other celestial bodies. This phenomenon not only demonstrates the precision of pulsars, but also opens the door to new ways of understanding the universe. Moreover, there is an even more intriguing aspect, the possibility that some pulsars are linked to cataclysmic events in the universe. For example, it has been suggested that supernova explosions can generate pulsars, but the exact process of their formation remains a mystery. What conditions are necessary for a neutron star to become a pulsar and not another type of cosmic object? As we investigate these enigmas, we must also consider the role that pulsars play in modern cosmology. Their existence and properties allow us to study the expansion of the universe and the nature of gravity. But what else could they reveal to us about the structure of the cosmos? Each new discovery about pulsars raises more questions than answers, leading us to reflect on our understanding of the universe. Finally, as we advance in the study of these stars, we face the reality that there is still much to discover. Each pulsar is a reminder of how little we know about the cosmos and how many secrets are still waiting to be revealed. The precision of these celestial objects can be astonishing, but it is also a symbol of the mysteries that still surround us in the vast universe. What surprises does the future hold in our quest to understand pulsars and, ultimately, the universe as a whole? Neutron stars are true wonders of the universe, but there is one aspect that remains an enigma: their surface. What is really on the surface of these mysterious entities? Is it solid, liquid, or something completely different? The answer to these questions is not only fascinating, but could also revolutionize our understanding of physics. Often, a neutron star is thought of as a compact and dense object, the result of the collapse of a massive star after its explosion as a supernova. However, what happens on its surface is much more complicated than it seems. Some theories suggest that the surface could be composed of a layer of superfluid matter, something that challenges our usual understanding of the states of matter. But how can we be sure of this if we have never been able to directly observe a neutron star? Imagine a sphere the size of a city, but with a mass that exceeds that of the Sun. Such compaction is enough for gravity to be so intense that the behavior of matter becomes strange. It has been proposed that on the surface of these stars, matter behaves very differently than it does here on Earth. Could there be a kind of crust that acts as a protective shield, hiding what is really beneath? The idea that the surface is a boundary between the known and the unknown is incredibly intriguing. Another question that arises is the temperature of the surface. Is it really hot or cold? It has been estimated that the surface temperature of some neutron stars can reach millions of degrees. which seems contradictory, as at the same time it is thought that their surface may be extremely cold. This clash of ideas raises the possibility that what we perceive as temperature is just a manifestation of the strange physics that governs these celestial bodies. But how can something so distant and in such extreme conditions be measured? In the context of the evolution of a neutron star, the question of its surface becomes even more relevant. As these stars age, they cool down, and many scientists wonder what happens to the structure of their surface as they lose energy. Does it break down, transform, or remain intact? The possibility that different layers of matter exist on the surface of these stars opens the door to a deeper understanding of what constitutes their nature. Scientists have introduced models suggesting that the surface may not be a single layer, but a complex system of interactions between different states of matter. What if we could see through that surface and explore what really lies beneath? Perhaps we would find a completely different world, where the rules of physics as we know them do not apply. This is the kind of scientific adventure that leads us to question our deepest beliefs about the universe. The mystery of the surface of neutron stars also has implications for the search for life beyond our planet. If matter in these stars can exist in forms we have never imagined, could there be some form of life that adapts to such extreme conditions? Although this idea may sound far-fetched, it reminds us that nature has surprising ways of adapting to hostile environments. This dilemma about the surface also relates to the question of how neutron stars behave at different stages of their life. Does the surface change as the star ages? The answer may help us better understand not only neutron stars but also other celestial bodies. Astronomers have been studying these stars closely, using advanced telescopes and observational technologies that allow them to capture their emissions. However, each new discovery raises more questions than answers. Are we really closer to understanding what is on the surface of a neutron star, or are we simply opening new doors to even greater mysteries? At the heart of all this uncertainty lies a fundamental truth. The universe is a place full of secrets, and neutron stars are some of its most intriguing pieces. Each attempt to unravel their mysteries brings us a little closer to understanding physics and the nature of the cosmos. But will it be possible that we never come to know the complete truth about the surface of these enigmatic stars? As we reflect on these topics, it is important to remember that science is a journey, not a destination. Each discovery pushes us to keep exploring, to keep questioning. The surface of neutron stars invites us to keep dreaming, to imagine what could be there in the unknown. Perhaps one day, we will unveil this enigma and discover the true nature of these fascinating cosmic entities. Who knows what other secrets await us in the vast and mysterious universe? Neutron stars are just one of the many questions that remain to be answered. Human curiosity is insatiable, and perhaps as we advance in our understanding, we will discover that what we think we know is only the tip of the iceberg of a much deeper knowledge. So keep your eyes on the sky and never stop wondering what mysteries may be waiting for us among the stars. In the vast universe of neutron stars, there is a phenomenon that has left scientists perplexed: glitches. What exactly are these sudden changes in the rotation speed of these stars, and why do they occur? This enigma has become a crucial point of interest in modern astrophysics. When we observe a neutron star, we often see it spinning steadily, like a cosmic lighthouse emitting regular pulses of radiation. But suddenly something surprising happens. The star may unexpectedly accelerate or decelerate its rotation. This phenomenon is known as a glitch, but how is it possible that a star with such intense gravity, which seems to operate so predictably, can experience such changes? Most glitches occur in pulsars, which are rapidly spinning neutron stars that emit radiation at regular intervals. However, these interruptions in their rhythm are anything but ordinary. One moment they are spinning at an impressive speed, and the next their rotation is drastically altered. What causes these changes? This is where the mystery begins. One theory suggests that these glitches are related to the movement of matter inside the neutron star. It is believed that these stars are composed of an incredibly dense core where pressure and temperature are so extreme that matter behaves in ways that challenge our intuition. Could it be that as matter redistributes within, it affects the rotation speed? Another hypothesis proposes that these changes could be linked to the interaction between the star's outer layer and its inner core. As the core spins and behaves dynamically, it may influence the rotation of the outer layer. But even with these theories, scientists have yet to find a definitive answer. How is it possible that such a simple and regular phenomenon like rotation can become so chaotic? Glitches are more than mere curiosities. They are keys to understanding how these stars work and what lies within them. Every time a glitch is recorded, a new window opens to understanding the behavior of matter under extreme conditions. But why do not all pulsars experience glitches? What determines whether a neutron star will have its rotation altered or remain stable? Some researchers have begun to think that glitches may be related to the star's history. Neutron stars, after their formation, undergo various processes that can influence their internal structure. Perhaps older stars, which have had more time to evolve, are more prone to experience these changes. Could this mean that the age of a neutron star is a determining factor in its behavior? Glitches also offer us clues about the nature of matter in the cores of these stars. If we consider that neutron stars are largely composed of neutrons, quantum mechanics plays a crucial role in their functioning. How do neutrons behave under extreme pressure conditions? The answer to this question could reveal not only the secrets of glitches but also fundamental aspects of physics. Moreover, glitches may be related to the star's interactions with its environment. When a neutron star is in a binary system, it absorbs material from a companion star. This process can influence its rotation speed and, therefore, cause glitches. Are these events connected to the life of the neutron star in a binary system? The answer could shed light on how these stars interact with their surroundings. It has been observed that some glitches are larger than others, generating more drastic changes in the star's rotation. What could be behind these variations? Some scientists believe they may be related to the accumulation of matter inside the star, which could lead to a redistribution of angular momentum. Each glitch, then, would be a window into an event occurring deep within the star. The importance of understanding glitches goes beyond scientific curiosity. These phenomena can provide insights into the evolution of neutron stars and, at the same time, give us clues about the nature of matter in the universe. What secrets lie hidden in the sudden rotation changes of these stars? The answers could change our understanding of the cosmos. As scientists continue to investigate glitches, it is clear that they are a fascinating mystery that invites us to explore further the workings of neutron stars. Each discovery in this field not only brings us closer to solving this enigma, but also offers us a new perspective on the universe we live in. What other mysteries lie hidden in the darkness of space, waiting to be revealed? Only time will tell. Neutron stars are fascinating creatures of the universe, and among their most intriguing secrets lies the enigma of zombie stars. What makes them come back to life after undergoing a supernova explosion? The answer to this question could lead us to understand cosmic processes that we have yet to fully explore. When a massive star reaches the end of its life, it collapses under its own gravity and explodes in a supernova. But not all neutron stars remain there. Some begin to absorb material from nearby companion stars, as if they were cosmic vampires. This process is known as reanimation. But how does this absorption occur? And what effects does it have on the neutron star? Astronomers have observed that as neutron stars come back to life, they can increase their mass and in some cases their rotation speed. But what does this mean for their existence? Neutron stars have a mass limit that, if exceeded, could transform them into black holes. So is it possible that these zombie stars are walking the thin line between cosmic life and death? The reactivation of a neutron star also raises questions about the material they absorb. By feeding on another star, what kind of material are they incorporating? The matter from these companion stars may be rich in hydrogen and helium, but it can also contain heavier elements. This process not only changes the neutron star, but can also trigger X-ray bursts that illuminate space. What do these explosions tell us about the chemistry of the universe? The idea of zombie stars also invites reflection on life and death in the cosmos. If these stars can come back to life, what does this mean for our understanding of stellar death? The transition from a neutron star to a black hole is not simply a change of state, it is a process that redefines our notion of what it means to live in the universe. Let's talk about pulsars, which are a specific type of neutron star that spin with astonishing precision. Some of these pulsars have been observed emitting regular bursts of radiation. If a neutron star can revive by absorbing material, could pulsars also experience this transformation? The answer may lie in the details of how these binary systems work and the gravitational interaction between them. Some researchers have hypothesized that zombie stars could be a source of energy for other celestial bodies. As a neutron star accumulates material, it generates intense radiation, which could influence the formation of new stars in its neighborhood. Could it be that zombie stars are not only coming back to life, but also giving birth to new stars? And let's not forget the role of gravitational waves in this scenario. When two neutron stars collide, they release an impressive amount of energy in gravitational waves. What happens to zombie stars in this context? Could these collisions be the result of interactions between neutron stars that have revived their lives? The discovery of zombie stars also has implications for our understanding of the universe's life cycle. If these stars can defy the norms of stellar life, what other surprises does the cosmos hold for us? There may be more mysteries to uncover that help us better understand the evolution of stars and matter in the universe. Furthermore, the existence of zombie stars could change our view on the formation of black holes. If these stars can increase their mass through absorption, what does that mean for the number of black holes that exist in the universe? Each zombie star that becomes a black hole adds a new element to the cosmic equation. Astronomers continue to investigate these phenomena, seeking answers to questions that so far remain unanswered. With each discovery, new doors open toward understanding neutron stars and the role they play in the universe. How many more of these zombie stars could be lurking in the darkness of space? The study of zombie stars is not only fascinating from a scientific perspective, but also invites us to reflect on the very nature of the universe. What does life and death really mean in a cosmos where some stars can defy their fate? This mystery continues to intrigue astronomers and researchers, and each new finding could change our perception of the universe. In conclusion, zombie stars are a reminder that the cosmos is full of surprises. Each neutron star that revives is a testament to the complexity and beauty of the universe. As we continue to explore these celestial wonders, we come a little closer to unveiling the secrets that have remained hidden for millennia. The story of zombie stars is just one chapter in the vast book of the universe, and many pages are yet to be written. What is at the heart of a neutron star? This is a question that has fascinated astronomers and physicists for decades. When observing these stars, one might wonder, how can such a small object, no larger than a city, contain such a vast amount of mass? Inside, it is believed that matter is compressed in such a way that extreme conditions are formed, far beyond what we can imagine. But what does dense nuclear matter really mean? When we talk about dense nuclear matter, we refer to a state of matter in which atomic nuclei are so close to each other that the forces holding them together become incredibly intense. But what does this imply for the structure of a neutron star? Some scientists suggest that in its core, the density is so high that a spoonful of this matter could weigh millions of tons. Can you imagine that? A tiny amount of matter capable of outweighing an entire building. However, the most intriguing aspect is the nature of this matter. It is believed that in neutron stars, neutrons cluster in ways we cannot observe under normal conditions. What happens if the pressure is so high that neutrons turn into quarks? the even more elementary particles that make up neutrons and protons. This is a fascinating concept, as it suggests that we might be facing a new state of matter that we have never seen before. But what does this mean for our understanding of the universe? The idea that strange quarks exist inside neutron stars opens up a range of possibilities. These quarks, which have properties different from those we know, could give rise to new types of matter. But how can we study something that is so far away and cannot be observed directly? Scientists use theoretical models and simulations to try to unravel these mysteries. However, the truth is that we are still in the infancy of our understanding of dense nuclear matter. And what about the influence of this matter on the gravity of the neutron star? The immense gravity they generate may be the result of this extreme density. But why is it so important to study this? By understanding how matter behaves in these extreme environments, we can learn more about the fundamental forces that govern our universe. Every discovery in this field could be the key to solving even greater enigmas. One of the most pressing questions is, will we ever be able to see or touch this matter? The answer for now is no. The matter inside a neutron star is trapped in conditions that are impossible to replicate on Earth. But that doesn't stop scientists. They continue to seek ways to infer its existence through indirect observations. How does this relate to the phenomena we observe in the cosmos? Astronomers have detected gravitational waves and gamma-ray bursts that could be related to events involving neutron stars. These signals are like echoes from the past, bringing us information about processes we cannot observe directly. So the question persists, what secrets do these stars still hide? Moreover, dense nuclear matter could be a key ingredient in understanding the evolution of the universe. Neutron stars are the result of the death of massive stars, and their existence affects the formation of new elements. But what role do they play in the creation of heavy elements like gold and platinum? This is a puzzle that scientists are trying to solve. With each new investigation, we delve into unknown territory. Dense nuclear matter not only challenges our notions of physics, but also invites us to question our understanding of the cosmos. What else is there to discover inside these stars? The search for answers continues, and each new finding could have implications we haven't even begun to imagine. Human curiosity drives us to keep exploring, to keep asking, what mysteries will dense nuclear matter reveal to us in the future? Science is an endless journey, and each new discovery is another step toward understanding our universe. So as we look up at the starry sky, let's remember that each tiny twinkle could be holding secrets of the matter that makes up the heart of neutron stars. Dense nuclear matter is just one of the many facets of these fascinating stars, but it has the power to change our perception of what we think we know. How will this change our view of physics and the cosmos in the coming years? Only time will tell, but one thing is for sure. The journey to understand neutron stars has only just begun. Each question leads us to new answers, and each answer invites us to ask even more questions. So, as we continue exploring, let's keep our minds open and our curiosity alive. The mysteries of the universe are vast and complex, and each of us has a role to play in this quest for knowledge. Dense nuclear matter is just a part of a much larger puzzle, and together we will continue to unravel the secrets that neutron stars have to offer. The ultimate fate of neutron stars is an enigma that fascinates astronomers and curious minds alike. What happens to these extraordinary entities when they exhaust their energy and approach the end of their life? In the vast universe where the rules of physics seem to play with us, the possibilities are as intriguing as they are varied. One of the questions that arises is, can all neutron stars become black holes? Or on the contrary, is there an alternative path that allows them to extinguish in a different way? To begin with, let's consider how these mysterious stars form. They are the result of the collapse of massive stars, which, after a cataclysmic explosion, leave behind an extremely dense core. But as the years go by and energy dissipates, what changes occur within? It is possible for a neutron star to reach a point where its mass and density change, which could determine its final fate. But how is that change measured? And more importantly, What does it really mean? One of the most accepted theories suggests that if the mass of a neutron star exceeds a certain limit, known as the Tolman-Oppenheimer-Volkoff limit, gravity becomes so intense that nothing can stop the collapse into a black hole. However, this limit is not clearly defined. How close are we to understanding it? Have scientists managed to calculate it accurately, or is there still a margin of error that leaves us in the dark? As neutron stars age, their radiation dissipates and their energy is depleted. But what exactly happens in those final moments? Is it possible that some of them find a way to avoid total collapse? There are theories suggesting that, under certain conditions, a neutron star could lose mass through a material ejection process which could temporarily stabilize it. However, this idea also raises more questions. What factors would allow this to occur? Would it be a rare phenomenon or a more common possibility than we think? Some scientists have proposed that instead of becoming black holes, some neutron stars could transform into even more exotic objects. For example, the matter that composes a neutron star could reorganize in such a way that it forms an unknown state, different from what we have observed so far. What kind of matter could arise from this transformation? How would this affect our understanding of the universe? But not all destinies are so grim. There is evidence suggesting that some neutron stars may simply turn off. This could happen without becoming black holes, leaving behind a trail of mystery and unanswered questions. Imagine a neutron star after living its life slowly disintegrating into a cloud of particles, disappearing from our universe silently. What implications would this have for our understanding of the stellar life cycle? The uncertainty surrounding the final fate of neutron stars is also reflected in how we observe these phenomena. Sometimes signals are detected that seem to indicate that a neutron star is in the process of decomposing, but the details are elusive. Could we be observing the final stage of these stars without realizing what is really happening? And if so, what prevents us from discovering it? Moreover, neutron star mergers are a phenomenon that has captured the attention of many. When two of these stars collide, they produce gravitational waves that offer us clues about their nature and behavior. However, the outcome of these mergers also raises questions. Do they become black holes, or are there other possible destinies that we have not considered? Are we on the verge of discovering new types of celestial objects thanks to these collisions? Meanwhile, research continues. Each new observation and each new discovery contributes to our collective understanding. Neutron stars are a fertile field for curiosity, and although we do not have all the answers, each question brings us a little closer to the truth. As science advances, so does our ability to unravel the secrets of the cosmos. And while the final fate of neutron stars may remain uncertain, the search for answers does not stop. Researchers continue to explore, posing new hypotheses and experimenting with models that help us better understand these phenomena. In this journey into the unknown, each discovery is another step toward enlightenment. So, as we continue to gaze at the night sky, let us remember that each neutron star is a reminder of what we still have to discover. Its final fate may be a mystery, but that only fuels our curiosity and desire to understand the universe we live in. Each star, each pulsar, each collision is a story waiting to be told, and perhaps one day we will unravel the enigma surrounding neutron stars. The journey has only just begun. Around some neutron stars, mysterious signals have been recorded that have left scientists perplexed. What exactly are these cosmic echoes, and where do they come from? The answer could open the door to phenomena that we do not yet fully understand. These signals, often in the form of electromagnetic radiation, seem to arise from sources that challenge our current explanations. But are they simply cosmic noise, or is there something deeper at play? Astronomers have detected bursts of radio waves that appear to originate from these enigmatic stars. Some of these signals are repetitive, while others appear in isolation. What do these differences mean? The radio waves reaching our planet could be the echo of cataclysmic events or interactions within the stars, but the mystery persists. Could it be that these signals are the result of phenomena we have yet to imagine? Neutron stars are known for their intense gravity and magnetic fields, making them natural laboratories of extreme physics. Amidst this complexity, the signals they emit could reflect processes occurring on scales that our minds can barely conceive. For example, it has been speculated that gravitational waves generated within them could be linked to these echoes. Are we facing the possibility that these mysteries are related to the very structure of space-time? As scientists study these signals, they wonder if they could be related to the formation of elements in the universe. Is it possible that neutron stars are a kind of cosmic forge, creating elements from the explosions and fusions occurring within them? The idea that these stars are not only a final destination for the collapse of massive stars, but also a place where new materials are generated is fascinating. Some signals have been so powerful that researchers have questioned whether they are unique events or continuous processes. What kind of energy is needed to generate such explosions in space? The search for answers has led scientists to develop new technologies and observational methods, but each discovery seems to raise more questions than it answers. Will these tools finally reveal the origin of the cosmic echoes? One of the most intriguing aspects is that these signals can occur across a variety of wavelengths, from radio to X-rays. What might this diversity mean? The variability in the frequency and intensity of these signals suggests that there is a complexity in the behavior of neutron stars that we do not yet fully understand. Each new finding could be the key to unraveling a part of the universe that has been hidden from us. The cosmic echoes have also led researchers to ponder the possibility of life or intelligence in other parts of the universe. Could these signals be a form of intergalactic communication, even if we do not understand their language? The idea that the cosmos is filled with messages waiting to be deciphered adds another layer of mystery to our exploration of space. How far will this quest for answers take us? Meanwhile, astronomers continue to monitor these stars and their signals, hoping to capture something that might provide more information. What technologies and scientific advancements can help us better understand these echoes? Science progresses, and with it, our understanding of the universe. Each new discovery has the potential to change our view of the cosmos. It is essential to remember that each detected signal is a reminder of the vastness of the universe and how little we truly know. Neutron stars and their cosmic echoes are just a small part of a much larger puzzle. What other wonders await us in the darkness of space? Human curiosity drives us to keep searching and questioning, as each new answer leads us to new questions. So, as we continue to explore, it is vital to keep an open mind and a curious spirit. What other secrets do neutron stars hold within them? Could the answers to these enigmas change our perception of physics and cosmology? As science advances, perhaps we will soon obtain answers that have eluded humanity for centuries. Each echo, each signal, each discovery brings us a little closer to unraveling these mysteries. But it also reminds us that the universe is a place full of surprises and that there will always be more to learn. The pursuit of knowledge is endless, and perhaps that is what makes the exploration of the cosmos so exciting. Neutron stars with their echoes and mysteries are a testament to the power of human curiosity. As we continue our quest, it is possible that one day we will understand not only the nature of these signals, but also the role they play in the vast tapestry of the universe. Are we ready to discover what lies hidden in the darkness? The adventure is just beginning. Neutron stars are one of the most intriguing phenomena in the universe, and among their mysteries, a fascinating question stands out. Why do they cool faster than scientists expected? This enigma, known as the cooling paradox, leads us to explore the depths of these extremely dense stars and to question what we know about their behavior. First, let's talk about how a neutron star is formed. After a supernova explosion, the core of a massive star collapses under its own gravity, resulting in a neutron star. In this process, unimaginable temperatures and pressures are generated, allowing matter to be compacted to extreme levels. However, what is perplexing is the cooling pattern we observe in these stars. When astronomers study neutron stars, it is expected that their temperature will gradually decrease over time. But what happens in practice? Many of these stars seem to lose heat much more quickly than anticipated. This phenomenon raises a series of intriguing questions. What is happening inside them? Are there processes we have yet to identify that are influencing their cooling? One of the most discussed theories suggests that in the core of these stars there may be exotic particles that we do not fully understand. The matter inside a neutron star does not behave like the matter we know. As a neutron star ages, its core is expected to cool. But what if there is an interaction between particles that acts as a more efficient cooling mechanism? Additionally, the possibility has been raised that neutron stars contain superfluids within them. Superfluids are states of matter that can flow without resistance and could be present under the extreme conditions of a neutron star. If this is true, they might facilitate a rapid loss of energy, which would explain the cooling paradox. On the other hand, some suggest that the magnetic field of a neutron star may play a crucial role in its cooling. These magnetic fields are extremely powerful, and by interacting with matter, they could influence how heat is distributed on their surface. But how does this connect to the cooling anomaly? Without a clear answer, the mystery deepens. As we explore these theories, another intriguing question arises. Could neutron stars have a more complex internal structure than we think? The idea that their core might be composed of different layers with distinct physical properties offers a new perspective on how they behave. This complexity could be behind the acceleration in their cooling. Observations have also shown that not all neutron stars cool in the same way. Some seem to follow the expected pattern, while others cool surprisingly quickly. What factors could be influencing these differences? Variations in their mass, magnetic field, or even the star's previous history could determine how they experience cooling. The study of the cooling paradox also raises a broader question about our understanding of the universe. If neutron stars are challenging our expectations, what other surprises does the cosmos hold for us? This mystery not only invites us to investigate further, but may also open the door to unexpected discoveries about fundamental physics. As scientists continue their research, efforts are being made to develop more accurate models that can explain the cooling of these stars. Collaboration between astrophysicists and particle physicists is essential to tackle this enigma and expand our knowledge of the universe. Despite all the advancements, the cooling paradox remains a mystery. It reminds us that no matter how much we learn, there will always be more to discover. Neutron stars, with their extreme and mysterious nature, are a constant reminder that the universe holds secrets that are still waiting to be revealed. In conclusion, the accelerated cooling of neutron stars is a phenomenon that challenges our expectations and invites us to keep exploring. The search for answers not only brings us closer to a better understanding of these fascinating stars, but also leads us to reconsider what we know about physics and the universe in general. The cooling paradox, like many other mysteries, is an opportunity for human curiosity to drive us to continue probing the unknown. Neutron stars are one of the most fascinating phenomena in the universe, and among their mysteries, one of the most intriguing is that of their enigmatic atmospheres. What is really in the thin layer surrounding these dense and compact stars? Science has made some strides in understanding it, but we still have a long way to go. First, let's talk about the structure of these atmospheres. Unlike more common stars, where gas and light mix in thick, bright layers, the atmospheres of neutron stars are surprisingly thin, just a few centimeters thick. But how can a star, which is so massive and dense, have such a light atmosphere? The answer seems to lie in its incredible gravity. That force is so intense that it crushes the matter around it, creating an atmosphere that challenges our usual understanding of what a star should be. Imagine that as you approach a neutron star, the first thing you would notice would be an environment completely different from any other star. The atmosphere could be composed of exotic elements that we have never seen on Earth. But what kind of elements? Some scientists believe there could be helium and even carbon, but in forms we cannot replicate. This raises a fascinating question. Are we facing a natural laboratory of physics and chemistry that can teach us about the extreme conditions of the universe? Moreover, the temperature in these atmospheres can be extremely high, reaching millions of degrees. However, it has been shown that despite this scorching heat, these layers are so thin that they may not be what they seem. Could we be underestimating their complexity? Science suggests that the atmospheres of neutron stars could be subject to phenomena that we have not been able to observe in other stars. An intriguing aspect is how these atmospheres interact with the surrounding environment. As neutron stars spin at incredible speeds, their atmosphere could be subjected to shear forces that affect its structure and composition. Could these forces be responsible for some of the phenomena we observe, such as gamma-ray bursts or radio emissions coming from these stars? It is also interesting to think about how the composition of these atmospheres could influence the radiation they emit. The light and other forms of energy escaping from a neutron star pass through this thin layer and can be altered on their way to us. This raises the question, what secrets could these alterations reveal about the nature of matter under extreme conditions? The mysterious composition of a neutron star's atmosphere also raises questions about the life cycle of these stars. When a massive star exhausts its fuel and collapses into a neutron star, what happens to the outer layers that were once part of it? Do they become part of this thin atmosphere, or are they expelled into space? This process could be key to understanding how these stars form and evolve. Astronomers are also intrigued by how the atmospheres of neutron stars can be affected by their environment. For example, when a neutron star interacts with another star, it could draw material from the latter, feeding its atmosphere. How would this affect its composition and behavior? The dynamics of these interactions is an active field of study that promises new revelations. A fascinating phenomenon is the possibility that the atmosphere of a neutron star is in equilibrium with the gravitational forces acting on it. Is it possible that this atmosphere is a reflection of the star's own history, telling us about its past and the processes that have shaped its existence? Each neutron star could be a time capsule, preserving valuable information about its evolution and the environment surrounding it. Research on the atmospheres of neutron stars also leads us to consider how they influence the propagation of gravitational waves. Since these stars are extremely dense and their gravity is incredibly strong, any change in their atmosphere could have significant effects on the space-time around them. Could we be observing not only the stars themselves, but also the echoes of their atmospheres in the gravitational waves traveling through the universe? As we advance in the exploration and analysis of these atmospheres, technology also plays a fundamental role. Advances in telescopes and observation techniques allow us to capture signals that were previously invisible. This leads us to wonder what unexpected discoveries await us in the future. Perhaps there are phenomena in the atmospheres of neutron stars that we have not even begun to imagine. In conclusion, the atmospheres of neutron stars are a mystery that continues to challenge scientists. Although we have made progress in understanding them, there is still much to discover. Each new observation could open the door to a deeper understanding of the physics of the universe and how stars form and evolve under extreme conditions. As we continue to explore, every answer we find raises new questions, keeping the wonder alive for these incredible cosmic objects. How powerful can magnetic fields be? In the universe, there is a type of neutron star that challenges our understanding, magnetars. These celestial objects possess magnetic fields that are millions of times more intense than that of our own planet. To put this in perspective, imagine the Earth's magnetic field as a gentle breeze. In comparison, that of a magnetar is a thunderstorm capable of tearing apart any known material. But why are they so fascinating? The nature of these extreme magnetic fields remains a great mystery. They are believed to be generated from a process called magnetic differentiation that occurs in the star's core. As the neutron star forms, its core spins and cools, which could amplify its magnetic field. But how is it possible for such a small and dense object to have such a colossal magnetic force? The answer may lie in the physics of neutrons themselves. which behave strangely under conditions of extreme gravity. What happens if you are near a magnetar? The answer is that being just a few 100,000 kilometers away from one could be lethal. The intense radiation they emit could destroy electronic devices and even affect the DNA of living beings. But can a magnetic field be so powerful that it even alters time and space around it? Scientists believe so, and this opens the door to new theories about relativity and how the fundamental forces of the universe work. As we investigate more about magnetars, we find that they are also capable of releasing enormous bursts of energy in the form of gamma rays. These explosions are so powerful that they can be detected billions of light years away. But what causes these explosions? Some researchers suggest that they could be the result of instabilities in their magnetic field that trigger violent eruptions. However, the precise details of this phenomenon remain a mystery. The relationship between magnetars and neutron stars is a topic that intrigues astrophysicists. Are all magnetars a kind of neutron star, or are they a completely distinct phenomenon? It is thought that most magnetars are, in fact, neutron stars that have developed extraordinarily strong magnetic fields. But what makes some become magnetars and others not? The answer may lie in the history of each star and the events they experienced before becoming what they are today. Another fascinating aspect is the effect that these magnetic fields have on their immediate surroundings. Magnetars have been observed to influence the formation of new stars. How is it possible for such a powerful magnetic field to affect other stars in its vicinity? The answer suggests that magnetars can generate stellar winds that alter the surrounding matter, creating conditions favorable for the formation of new stars. This raises intriguing questions about the influence of these stars on the evolution of the universe. As we continue to explore these mysteries, scientists face a challenge: how to study something so distant and powerful. Despite technological advancements, magnetars remain difficult to observe and understand. What tools could help us unravel their secrets? Gamma-ray telescopes and other advanced instruments are at the forefront of this research, but there is still much to learn. The nature of the magnetic fields of magnetars also raises questions about matter under extreme conditions. What kind of particles could exist inside them? Some scientists suggest that in their core, neutrons might behave very differently than they do under normal conditions. This leads us to consider the possibility that there are forms of matter we have yet to discover, which could change our understanding of physics. While most neutron stars are extremely dense, magnetars stand out for their extraordinary combination of density and magnetism. This raises the question of whether there are other similar phenomena in the universe. Could there be other types of stars that also possess unusual characteristics that we have yet to identify? The answer could lead us to new frontiers in astronomy. Every time a magnetar emits a gamma-ray burst, scientists have the opportunity to study its behavior. However, each event is unique and presents a new set of challenges. How can we predict when the next explosion will occur? This is a question that keeps astronomers on constant alert, as each flash could reveal crucial information about the universe. The study of magnetars also leads us to reflect on the future of the universe. If these bodies are capable of influencing the formation of new stars, what role will they play in the evolution of galaxies? This makes us think about the interconnectedness of all celestial bodies and how, despite their distance, they are all related in a complex cosmic dance. As we delve into the mystery of magnetars, we realize that each answer generates new questions. The exploration of these phenomena invites us to expand our imagination and question what we think we know about the universe. What will be the next great discovery that reveals more about these fascinating celestial bodies? The future of astronomical research is full of possibilities, and each new answer may lead us to an ocean of even deeper questions. Thus, magnetars stand as some of the most intriguing mysteries of the universe. As we continue to study their nature and effects, we get a little closer to understanding not only these stars but also the cosmos as a whole. The pursuit of knowledge is an endless journey, and magnetars are just one of the countless stops on this fascinating journey through the mysteries of the universe. Neutron stars are one of the most fascinating phenomena in the universe, but within their incredible density lies an even greater mystery: strange quark matter. What exactly are strange quarks and why are they so intriguing? To understand this, we must first remember that everything in the universe is made of subatomic particles. Protons and neutrons, which make up the nucleus of atoms, are composed of quarks. There are 6 types of quarks, with the most common being up and down quarks. However, strange quarks are different. Why are they named that way? Because they are unusual and found in extreme conditions. Can you imagine being in a place where gravity is so intense that matter behaves in ways we have never seen on Earth? Inside a neutron star, the conditions are so extreme that strange quarks are believed to potentially form a new phase of matter. What if, in the core of these stars, where pressure and temperature are unimaginable, strange quarks group together differently? This idea has led scientists to explore a new form of matter that could be completely foreign to what we know. The theory suggests that as a neutron star collapses, some of its matter may convert into this form of strange quarks, creating what is known as a quark star. But does a quark star really exist? Although we have not been able to directly observe this type of star, simulations and theoretical models suggest that they could be a reality. But how do these quark stars behave compared to normal neutron stars? The main difference lies in the composition of their matter. While neutron stars are primarily composed of dense neutrons, quark stars could be more complex and potentially more unstable. Imagine a star that is not only incredibly dense but also has completely different properties, which could affect its evolution and ultimate fate. One of the most intriguing questions is, how can we detect these mysterious quark stars? The answer is not straightforward. Although there is no direct evidence of their existence, astronomers are searching for signals in the universe that could indicate their presence. For example, gravitational waves generated by the collision of neutron stars could provide clues about the extreme conditions inside these stars. If anomalies are detected in these waves, they could be an indication that strange quarks are involved. What is fascinating about this search is that it not only helps us understand neutron stars, but also gives us a broader insight into the nature of matter in the universe. What other forms of matter might exist that we have yet to discover? The existence of strange quarks could revolutionize our understanding of physics and how objects in the cosmos are formed. Moreover, strange quark matter raises questions about the stability of neutron stars themselves. If they do exist, would they destabilize over time? Could they potentially become black holes more quickly? Each new answer we find generates more questions, and that is what makes the study of these stars so exciting. Imagine for a moment what it would mean to find a quark star. It would mean that we are on the frontier of new knowledge, a new chapter in the history of astronomy. The search for these stars leads us to question what we thought we knew about matter and physics. Are we ready to challenge our notions of what is possible in the universe? The possibility that quark stars exist also leads us to rethink the nature of dark matter, that mysterious substance that makes up a large part of the universe but still eludes us. Could it be that quark stars are a component of this dark matter? Could they be the key to unraveling one of the greatest enigmas of modern cosmology? As we continue our exploration of the cosmos, each discovery brings us a little closer to answering these questions. Science advances by leaps and bounds, and each new space mission, each new telescope, and each new experiment in laboratories provides us with tools to deepen our understanding. The search for strange quark matter is just one of the many adventures that await us. In summary, strange quark matter represents a fascinating mystery that is yet to be solved. The possibility that it exists within neutron stars not only reconfigures our understanding of matter, but also opens the door to new theories about the universe. Each discovery in this field invites us to look up at the sky with wonder and curiosity, reminding us that there is still much to learn in this vast and mysterious cosmos we inhabit. Who knows what secrets the universe will reveal to us in the future? What happens when two neutron stars collide? The answer to this question is one of the most fascinating mysteries of the universe. Imagine two celestial bodies, each with a mass greater than that of our Sun, but compressed into a size no larger than a city. These stars, which are the remnants of supernova explosions, are so dense that a teaspoon of their material would weigh more than all the humans on Earth combined. But what happens when these colossal stars collide? When two neutron stars collide, a spectacular cosmic event occurs. This encounter not only releases an enormous amount of energy, but also generates gravitational waves. But what exactly are gravitational waves? They are like the echo of a stone thrown into water, but instead of waves on the surface of the water, they are distortions in the fabric of space-time. This phenomenon was theorized by Albert Einstein, but it wasn't detected until a few years ago. The collision of neutron stars was one of the first sources of gravitational waves that scientists were able to observe. In addition to gravitational waves, this collision can also lead to the creation of heavy elements such as gold and platinum. But how is it possible for these precious metals to form in space? When neutron stars merge, the extreme processes of temperature and pressure allow atomic nuclei to assemble in ways that cannot be replicated in Earth laboratories. Thus, the gold we find in our jewelry could have a cosmic origin born from the fusion of these titanic stars. Neutron star mergers are rare but incredibly powerful events. Did you know that it is estimated that these collisions occur approximately once every 1,000 years in our galaxy? However, each time one occurs, the resulting glow can be detected billions of light years away. This has allowed astronomers to study these phenomena, although there is still much to learn about them. Now let's talk about what happens at the moment of the collision. As the stars approach, their gravitational fields intensify, creating a cosmic dance that ends in an explosion. The energy released during this process is so immense that it can shine more brightly than an entire galaxy for a brief period. This flash, known as a kilonova, is one of the most exciting aspects of these mergers. But how do scientists detect these explosions? State-of-the-art telescopes, which can observe different wavelengths, play a crucial role. After gravitational waves are detected, astronomers point their telescopes to the region of the sky where the collision occurred. This way, they can see the glow of the kilonova and study the light it emits, allowing them to gather clues about the composition of the elements created in the process. However, despite all the advancements, there are still many unanswered questions. What exactly happens in the core of these stars during the merger? Some scientists believe that new types of matter could form, even exotic forms of quarks, which are the basic components of protons and neutrons. But how does this matter behave under such extreme conditions? The answer remains a mystery. The study of neutron star mergers has also opened the door to a new way of understanding the universe. Gravitational waves not only tell us about mergers, but can also reveal information about the structure of space-time itself. Each time a new signal is detected, scientists get excited, as it could be the key to unraveling the secrets of the cosmos. Even more intriguing is the fact that these mergers could help us understand dark matter and dark energy, two of the most mysterious components of the universe. The way these forces interact during a collision could offer clues about the nature of these entities that make up approximately 95% of the universe, but that we cannot see directly. As technology advances, scientists are getting closer to answering these questions. What discoveries await us in the future? The next time you look at the stars, remember that somewhere in the universe, two of them might be about to embark on a journey that will change our understanding of the cosmos forever. Meanwhile, each new collision and each new discovery brings us closer to understanding the very nature of the universe. Neutron star mergers are just one of the many wonders of the cosmos, but their study reminds us that, although there are mysteries we have yet to solve, each answer leads us to new questions and new adventures in the pursuit of knowledge. So when you think of space, remember that it is not just a dark void, but a place full of activity and wonder, where neutron stars collide and create not only precious elements, but also new horizons of understanding for humanity. The exploration of the universe is an endless journey, and each discovery invites us to dream of what is yet to come. How can a star be so powerful that its own gravity deforms it? Neutron stars are a fascinating cosmic phenomenon, and their incredible gravity can cause their shape to distort in ways we can barely imagine. But what does this really mean in terms of their geometry? As a neutron star forms, its core collapses under its own gravity. This process is so extreme that the matter within the star is compressed to unimaginable densities. But here's the intriguing part. Despite this compression, stars do not become perfect spheres. Instead, they deform slightly, taking on shapes that may appear more oval. This deformation is the result of the intense gravitational forces acting upon them. What causes this peculiar shape? The rotation of the neutron star plays a crucial role. When a star spins at high speed, the centrifugal force tends to make the equator bulge, causing its shape to resemble more of an oblate spheroid than a perfect sphere. But how much does this rotation really affect the star's shape? It is estimated that some of these stars can rotate more than 1,000 times per second. Imagine the energy and force involved in such movement. However, the story doesn't end there. What if I told you that extreme gravity not only affects shape but also how matter behaves inside? The gravity can be so intense that even light struggles to escape, meaning we cannot see inside these stars, but what is inside them? Although we cannot observe them directly, scientists have proposed theoretical models to understand how matter behaves under such conditions. As we delve into the mystery, even deeper questions arise. Could the deformed shape of a neutron star influence its gravitational field? If the shape of the star is not symmetrical, that could affect how it interacts with other stars and objects in space. This raises questions about how these interactions could influence the evolution of the universe. One fascinating aspect of this deformation is its impact on the detection of gravitational waves. When two neutron stars in orbit merge, the shape is not just a curiosity, it can affect how gravitational waves are emitted during the merger event. Could these waves help us solve the enigma of their shape? Scientists are working hard to unravel this mystery, and each new discovery could provide clues about how these stars function. Let's imagine for a moment the future. As technology advances, we may be able to observe more about these deformed stars. What other surprises does the universe hold in this regard? Human curiosity has always driven exploration, and every answer we find raises even more questions. The deformed geometry of neutron stars is just one of the many facets of their complex nature. What other characteristics might be hidden in their mysterious cores? The matter inside them could behave in completely different ways than we know. The physics governing these stars could be the key to unlocking secrets of the universe that we do not yet fully understand. In summary, the fascinating deformation of neutron stars is not just a visual phenomenon, but an indicator of the extreme forces at work in the cosmos. Each new discovery about their shape and behavior brings us a little closer to unraveling the secrets of the universe. Neutron stars, with their unique geometry, continue to be an intriguing field of study that challenges our understanding of physics and matter. So the next time you look up at the sky and think about the stars, remember that some of them are much more than just bright points. They are cosmic laboratories teaching us about the laws that govern the universe. Neutron stars are a reminder of the wonder of science and the eternal quest for human knowledge. What else will they reveal to us in the future? The answer lies in the stars, waiting to be discovered. Neutron stars are some of the most fascinating and mysterious objects in the universe, but did you know that there are phenomena in the cosmos that seem to be related to them and that we still do not fully understand? One of these enigmas is the fast radio bursts, known as FRBs. These radio signals have become the focus of many astronomers and researchers. What are these bursts really, and what is their origin? First, it is important to note that FRBs are bursts of energy that last only a few milliseconds. But what could cause something so powerful in such a short time? Some scientists have suggested that they might be related to neutron stars, specifically those that have extremely strong magnetic fields like magnetars. But how is it possible for a neutron star to generate these bursts? The most intriguing theory is that FRBs could be the result of violent events on the surface of these stars. Imagine a neutron star spinning at incredible speeds, generating a magnetic field so intense that it could affect the space around it. Could it be that at the moment a neutron star undergoes a change in its magnetic field? An explosion of energy is released that travels through the universe in the form of radio bursts. As astronomers have detected more of these bursts, they have begun to notice patterns. Why do they seem to occur in specific places in the sky? Is there something in common among the different FRBs we have observed? Some theories suggest that they could be related to the merger of neutron stars or even to the activity of nearby black holes. But how can we be sure that these connections are real? Another question that arises is, why are some bursts unique and do not repeat, while others seem to return at regular intervals? This behavior has puzzled scientists, and some think that there could be different types of sources behind FRBs. Could it be that some of these bursts come from young neutron stars, while others are the result of the collapse of older stars? Even more intriguing is the possibility that FRBs are related to astrophysical phenomena that we do not yet understand. There are theories suggesting that they could be the result of extreme cosmic events such as the collision of neutron stars or the explosion of supernovae. However, so far we have not been able to directly observe these events to confirm it. Are we facing a new frontier in the understanding of the universe? We must also consider that FRBs could have deeper implications about the nature of space and time. If they are linked to neutron stars, then they could offer clues about the physics that governs these objects. Could it be that by studying the bursts we are unraveling secrets about gravity, matter, and the very fabric of the cosmos? Research continues, and each new discovery brings us a little closer to solving this puzzle. However, they also raise more questions. What other mysteries might be hidden in the universe, waiting to be discovered through the observation of these bursts? Perhaps FRBs are just the tip of the iceberg in a sea of cosmic enigmas. As technology advances, new telescopes and methods are being developed to detect and study these bursts. What revelations will these new tools bring us? Each detection of a fast radio burst leaves us with more questions than answers, and that is what makes this field of study so exciting. Astronomers are not only focusing on FRBs but also trying to understand the context in which they occur. Are they related to the type of galaxies in which they are found? Are there patterns in their distribution across the sky? Every answer we find seems to open the door to more questions, creating a web of intertwined mysteries. At the end of the day, the study of fast radio bursts and their possible connection to neutron stars reminds us of how little we know about the universe. Every new signal we hear invites us to explore deeper, to question what we think we know, and to keep curiosity alive. What other secrets might be waiting in the vastness of space, ready to be discovered? So the next time you think about neutron stars and fast radio bursts, remember that we are in the midst of an exciting quest. Each discovery is another step toward understanding the mysteries of the cosmos, a journey that is just beginning. Can you imagine what revelations await us in the future? Science progresses, and with it, our ability to unravel the wonders of the universe. As we look into the vast universe, a question resonates in our minds. What secrets do neutron stars hold? These fascinating and dense cosmic spheres are like puzzles that we have yet to fully solve. As we delve into the mystery of their existence, another intriguing question arises. What can they teach us about the nature of the cosmos and the laws that govern it? Each neutron star is a spectacle in itself, spinning at unimaginable speeds and challenging our understanding of physics. But what lies behind their extreme rotation? Some scientists suggest that this speed may indicate something even deeper, a phenomenon that could change our perspective on time and space. Could these stars be sending signals from within, trying to communicate with us? As we explore their surface, we encounter another fascinating enigma. Do they really have a solid surface, or is their structure completely different? Imagine a sphere that does not behave like a rock but possesses strange properties. This mystery of the surface could hold clues about the matter that composes not only neutron stars but the entire universe. But how could we study something so distant yet so compact? We cannot overlook the enigma of glitches, those sudden changes in rotation speed that baffle astronomers. What dramatic force could be operating inside these stars to cause such alterations? These questions lead us to reflect on the nature of gravity and energy in such an extreme environment. Could it be that these events are echoes of some yet undiscovered phenomenon? As we delve deeper into their core, we encounter the densest matter we can imagine. But what does this mean for the composition of the universe? If neutron stars are like laboratories of cosmic physics, what experiments could we conduct through the observation of their behaviors? The density of their matter could be the key to understanding the formation of heavier elements, such as gold and lead. And speaking of elements, what happens when two neutron stars collide? This catastrophic event produces gravitational waves and surprisingly heavy elements, but the process of stellar fusion itself remains a mystery. How does the energy of the collision transform into matter? This phenomenon leads us to question the very essence of stellar creation. On the other hand, the gravitational oscillations occurring within them could be generating continuous gravitational waves. What implications would this have for our understanding of relativity and the fabric of space-time? As we explore these questions, we realize that each answer can open new doors to an endless array of mysteries. Another intriguing aspect is pulsars, which spin with almost mechanical precision. What mechanisms lie behind this regularity? Used as cosmic clocks, pulsars not only help us measure time in the universe, but also make us question whether there is an underlying order in the chaos of the cosmos. Could these stars be a reflection of the harmony of the universe as a whole? As we approach the conclusion of this journey, we cannot help but wonder about the ultimate fate of neutron stars. Will they all end up as black holes? Or will some extinguish in ways we cannot yet imagine? This questioning invites us to reflect on life and death in the cosmos and how each star, no matter how small, plays a role in the eternal cycle of creation. And we cannot overlook the mystery of cosmic echoes, those mysterious signals surrounding certain neutron stars. What phenomena could be behind these emissions? As science advances, each discovery may bring us closer to unraveling these enigmas. But each answer also generates new questions. Finally, when considering the cooling paradox, we face an even greater challenge. Neutron stars seem to cool faster than models predict. What unknown processes could be occurring within them? This phenomenon reminds us that the universe is a place full of surprises where each discovery can destabilize our most solid theories. So looking up at the sky, what does the future hold for us? Neutron stars are just a part of the cosmic puzzle. And as we continue to explore their mysteries, each step brings us closer to understanding the very nature of the universe. Human curiosity is a powerful force, and by probing these mysteries, we embark on a journey that could redefine our existence. In the end, neutron stars are not just celestial objects, they are beacons illuminating the path toward knowledge and wonder in the cosmos.